So time now to move on to part 3 of our proof of linearity. So we now have two functions, a function f and a function g, and both of them are assumed to be Riemann integrable over the interval ab. And we now want to consider the function f plus g, which takes any point x in the interval onto f of x plus g of x. And we want to prove that this function is Riemann integrable over that interval ab, and that the value of its integral is the value of the integral of f plus the value of the integral of g. So to show that this function f plus g is Riemann integrable, once again what we need to show is that the supremum over all dissections of the lower Riemann sums of the function f plus g is equal to the infimum over all dissections of the upper Riemann sums of f plus g. And then if that is the case, then the value of these two things is then the value of the integral of f plus g dx over the interval ab. Now, how are we going to do this? Well, what we know is that f and g are Riemann integrable. So to be able to show this, we need to relate the upper Riemann sums of f plus g and the lower Riemann sums of f plus g to the upper and lower Riemann sums of f and g separately. So let's just have a play around and see if we get anything that we can actually use. And this isn't too complicated. So let's consider the upper Riemann sum over some dissection d of f plus g. So again, we've got our arbitrary dissection d, and just so that we can actually write down what the sum is equal to, let's say it's splitting that interval ab up into n pieces. So this is going to be the sum from I is equal to 1 to n of xi minus 1 times the supremum of the value of f plus g at x, where x is allowed to vary over the elements in that interval, so the interval xi minus 1 to xi. Now, of course, f plus g at x is defined like so let's replace that with f of x plus g of x, like so. So this is the definition for the upper Riemann sum of f plus g over our dissection d. Now, the avenue to investigate hopefully is screaming out at you. It's to look at this thing. We want to somehow split this up into the supremum of f of x and the supremum of g of x. For instance, if we could split it up into supremum of f of x plus the supremum of g of x, then this whole sum would split into two parts, one part that's equal to the upper Riemann sum of f and another part that's equal to the upper Riemann sum of g. So that's what we would like to do. Now, how can we actually do that? Well, it's not the case that equality is going to hold true in general. So this we cannot just replace with supremum of f of x plus the supremum of g of x. Sometimes equality will hold, but in general that won't be the case. What will always be the case is that an inequality will hold true. This is always going to be less than or equal to the supremum of f of x, where x is allowed to vary over xi minus 1 to xi, plus the supremum of g of x, where x is allowed to vary over xi minus 1 to xi. Now, let me just give you some intuition for why that is the case, and then I'll prove it to you more rigorously. So if we have a little picture here, let's say this is our interval, xi minus 1 to xi here, and let's say we have a function f that looks like this, and let's say we also have a function g that might look like this. So just to label them up, that's the function f, that's the function g. Now, if you then look at what the supremum of f of x and the supremum of g of x are over those intervals, hopefully, I meant it to be the end points, to be simple. Now, my pictures aren't perfect, but hopefully they look reasonably like that is the highest point. So these functions that I've drawn are continuous over that closed interval. So by the extreme value theorem, they obtain a maximum and minimum. So the maximum value is going to be their supremum. So these points in green, these are the supremum. So this is supremum of f, this is supremum of g. When you then add the function f and g together, now I won't attempt to draw that, but of course it's going to look something like this. It would make, oh, it's not going to look like that actually. In fact, I might attempt to draw it. So it's not quite to scale, but it will look something like that maybe. So this is f plus g. So all I've done, and obviously it's not to scale perfectly, this should be higher in reality, but it would be up in the way of this. So all you do is for every single point x in here, you add the value of f to the value of g, and that's the point you plot on here. So you're just basically adding these two together. What you can imagine doing is taking this function f here, and then taking all of their heights and then sticking them on top of the function for g. So if, for instance, you had this height here for f at that point, then you need to kind of stick it on top of this, and then that point up there would have been the point for f plus g at that endpoint xi minus 1. And you can imagine doing that for every single one of the points and then building the graph. Now, when I've drawn it there, I've actually ended up drawing it higher than my blue line, but yeah, the picture's bad. But hopefully you understand what we're saying here. So in this case, the supremum of f plus g, again, it's going to be a nice continuous function, so it obtains its maximum and minimum, so it's going to be this maximum value up here, and that is just going to be the value of f plus g. Now to give you another example, where equality doesn't hold true, and I don't want to do it in yellow. Let's change back to white. So, again, here we have the interval xi minus 1 to xi. Now, the reason that the supremum of f of x plus g of x ended up just being the supremum of f plus the supremum of g is because they both had their supremum at the same value of x in the interval. If they didn't have their suprema at the same value in the interval, then that wouldn't be the case. So if instead we drew something like that for f and that for g, so this is f, this is g, then now you can see that if we took supremum of f plus the supremum of g, we would be adding that for the supremum of f to that for the supremum of g, so we'd get quite a high number. Whereas when we add these two functions together, what are we going to get? We're going to get something that might look a bit like that. It's going to be pretty level because they're kind of like complementary to one another, these two functions I've drawn. But the height of this isn't going to be the same as the height of f plus the height of the height of the supremum of f plus the height of the supremum of g. That's going to be up here. So hopefully that kind of illustrates why the equality doesn't always hold true, but you can see that this thing is always going to be bigger than the actual supremum or equal to it in this special case. So let's do that a little bit more abstractly and a little bit more rigorously now. So we want to show then that this number plus this number is greater than or equal to this supremum. Now, to understand what I'm about to do, it might actually help to write down what the set is that we're taking the supremum of here. So remember, that notation that we're using there is very slick, very nice, but what it really means is the supremum of this set in full. So we take all the values f of x plus g of x, where x varies over this interval, xi minus 1 to xi, and take the supremum of that set, and that's this number here. So we want to prove that that supremum is less than or equal to this. Now, one way we could do that, and the way we're going to do that, is to show that this is an upper bound for this set. So to show that these two numbers added together is greater than or equal to everything that is in that set. And the reason that would do is because it being an upper bound means that it is going to be greater than or equal to the least upper bound. So if it's an upper bound and it happens to be the least upper bound itself, then it will be equal to this. If it's an upper bound that's bigger than the least upper bound, then it will be greater than it. So by showing that this is an upper bound of this set, we will have shown that it is greater than or equal to the supremum of this set, i.e. the thing here in that inequality. So to show this inequality, all we need to do is show that these two numbers added together is an upper bound for the things in this set. So how are we going to do that? Well, hopefully you should be able to figure that out for yourself. So the way we do it is we note that this thing is going to be greater than or equal to f of x for all values of x in this interval. So for all x is an element of that interval, xi minus 1 to xi, I note that f of x is going to be less than or equal to the supremum of f of x as x is allowed to vary over xi minus 1 to xi. And that follows from the definition of this supremum. This is the supremum of f of x where x is allowed to vary over xi minus 1 to xi. So it is a upper bound for f of x within this interval. So all of the values of f of x in that interval are going to be less than or equal to this value. And similarly for the values of g of x, so again, I note that for all x is an element of the interval xi minus 1 to xi, that the value of g of x is going to be less than or equal to the supremum of g of x, where x is allowed to vary over that interval xi minus 1 to xi. Again, that's definition. All the values of g of x in this interval are going to be less than or equal to the supremum of the values of g of x in that interval. And now I can just combine these two inequalities together. So whatever x you take in this interval, this and this are going to hold true. So if this is less than or equal to this, and this is less than or equal to this, then if I add those two things together, f of x plus g of x, it's going to be less than or equal to these two things added together. So I now have that f of x plus g of x is less than or equal to the supremum, as x is allowed to vary over xi minus 1 to xi of f of x plus the supremum of g of x, again as x is allowed to vary over the interval xi minus 1 to xi. And that's exactly what I wanted to prove. This holds true for all x in that interval, so everything inside this set then is less than or equal to this value, supremum of f of x plus the supremum of g of x. Therefore, this thing is an upper bound for this set. Therefore, it is greater than or equal to the supremum of that set. Now, this argument holds true for every single one of these cut up intervals that my dissection has cut the interval AB into. So let's write this out now in full. So for all of those intervals that my dissection has cut the interval AB into, so for all I from 1 to n, so for all I is equal to 1 all the way up to n, this is going to hold true. xi minus 1 times the supremum x is an element of xi minus 1 to xi of f of x plus g of x is going to be less than or equal to the, well, xi minus xi minus 1. So what I'm doing is taking this inequality and just multiplying both sides by xi minus 1, and then I'll apply distributivity here to write it as two separate things. So times, and that's going to be this bit here. The supremum x is an element of xi minus 1 to xi of f of x plus xi minus 1 times the supremum of g of x, where x is an element of the interval xi minus 1 to xi. So for every single one of those bits that we've cut the original interval into, so from I is equal to 1 to n for our dissection D, this inequality holds true. And now, of course, what you can do is you can combine it together So we have one of these for each I, so you could substitute in I is equal to 1 here, it would be true. You could substitute in I is equal to 2 here, it would be true, all the way up to n. So we have n separate inequalities, and we're going to combine them all together into a sum to say that the sum of all of these bits is less than or equal to the sum of all of these bits. So if every single one of these bits is less than or equal to these two things, then when you sum all of these ones for I is equal to 1 to n, it's going to be less than or equal to all of these things summed from I is equal to 1 to n. But of course, when you sum all of these from I is equal to 1 to n, that is the definition for the upper Riemann sum of f plus g over our dissection D. So we'll get that the upper Riemann sum of f plus g over our dissection D is therefore less than or equal to, and then we've got these two separate sums that we're doing, the sum of this from I is equal to 1 to n, which is of course the upper Riemann sum over the dissection D of f, and then the sum of this from I is equal to 1 to n, which is of course the upper Riemann sum over the dissection D for g. And that is the inequality that we wanted, that the upper Riemann sum of f plus g is less than or equal to the upper Riemann sum of f plus the upper Riemann sum of g. It's an inequality relating upper Riemann sums of f plus g to the upper Riemann sums of f and the upper Riemann sums of g. We'll have a break here, and in the next video we'll derive the equivalent inequality for the lower Riemann sums.